So today we're going to look at the Kollmorgen motor with a BiSS-B feedback and a sine cosine. It's very interesting because most of the BiSS applications tend not to have sine cosine. But the sine cosine is good for getting a higher resolution by doing interpolation inside the drive. The BiSS-B on the Kollmorgen is 17 bits of positional information, which we'll use for velocity. And the sine cosine is 2048 lines, 8192 cycles of the sine or cosine per rev, which will interpolate times 4 and add a 4096 interpolation on top of that. We're going to be using a Xenus EtherCAT compact drive. I've got the stow bypass jumper installed to bypass the safety. I've got the 24 volts hooked up. There's no brake on this motor, but if there was, we could hook it up here. Got the motor power wired, UV and W, and I have the AC power, 120 volts AC. This can take 120, 240, 208, whatever your AC is. And the feedback device is wired and connected. I've also added an extra ground for the case to earth so that we can get the best EMI possible. I'm going to use a USB to serial adapter today, an Ellis Stream, USB to RJ11, and for my power supply Keep Alive, it's just a 24 volt DC power supply with like half an amp on it. So we'll take a look at the wiring diagram and how to use CME2 with this and configure it. So I've got the AKM selection guide here. It's a 2014 document. You can see the AKM, all the different frame sizes and options. This specification sheet contains all the inductance, resistance, torque constants, continuous currents, everything we need for the motor specification data. Plus it details the feedback devices that are options for this motor. And today we've got the AA, which says BiSS-C single turn or BiSS single turn. It's actually a BiSS-B, like a Hengstler device. And it does come with sine cosine. That's very familiar with like an NDAT 2.1 with sine cosine, but with the 2.1 you would need the sine cosine. With the 2.2 NDAT you would not need cosine, sine and cosine. And that's the same is true for the BiSS-B. You don't need the sine and cosine. We can do the interpolation on the 17 bits. It's like 5,000 counts per rev, which is plenty for position information. But if we want to try to increase the resolution, this is what we're going to hook up as the sine cosine. And I'll show you how to do that today. So I'm looking at the Xenus compact data sheet here, and it's showing the BiSS absolute encoder and how to wire it to the feedback connector. We have clock coming out of the drive. That comes out on the X and X naught and clocks out the data over the S and S naught. I've got +5 and ground connected. The motor has a sense plus and a sense minus. I'll double those up on the +5 and ground so that I have less IR drop over the cable length. And of course, make sure you hook up the shield to earth. The drive, the Copley drive, has pin 1 for the frame, so take the shield and connect that to pin 1. And for the sine cosine connection, we'll do the same thing we did for the NDAT. The shield hooked up, and we have sine plus, sine minus, cosine plus, and cosine minus connected to the drive with respect to the signal ground and the +5. So I'm using CME2 version 7.1, the latest beta, downloaded and installed, and I've got the drive configured from the motor specification. But I did want to show something about the feedback resolution. You can see we're holding position. Normally we hold position plus or minus a count, but we've got some ridiculous interpolation here to get us the resolution. It's like 33 million counts per rev. And sometimes, what do you get when you get more counts per rev? You get more following error. you also have more counts per rev for closing loops and stuff, so that's good. But just so you can see, when we're enabled, you get plus or minus maybe 100 counts, and then when we're disabled, there's still noise. I mean, this is an analog signal. It's susceptible to noise, and it's still going to have plus or minus about 100 counts of noise error based on the signal to noise ratio. And this Xenus Compact has, some of the best A to D converters. It's off chip. It's got a high E knob. So this is just the effect of interpolation, but it's fine. We're getting crazy resolution, and that's working for us really good. We'll show you how to do that too. So the first thing we look at on the basic setup is how to configure this sine cosine. We're going to say we have BiSS on the motor shaft, and we're going to say the load is the sine cosine. That's the analog feedback, and we'll use that to close the position loop. So technically speaking, the current and velocity loop are based on the motor absolute encoder. This is good for commutation, and it's also a reasonable 500,000 or more count for velocity loop tuning, which is perfect. And then the high resolution will come from interpolating the sine cosine. We can also, put it in the mode of operation we like, and we can emulate the encoder count output. That's from the load. That's the 33 million counts per rev, so we may want to divide that down if there's a controller that's looking at that too. But for the most part, just let the Copley close the position loop and read the position over the serial port or EtherCAT port or even the CAN port on a CAN drive. So we'll take a quick look at the configuration of the Kollmorgen feedback device. It does say 24 bits in the catalog, but it's really only 19 bits with 5 alignment bits that aren't used for anything. We select BiSS-B and we come up with 5,024,288 counts per rev. It's a single turn. If it was multi-turn, it would be a 4096. Probably has the Henksler with a mechanical device and no battery. And for advanced settings, we just want to use the default. And I'm going to update at the servo loop update. This should be the default setting here at 4 megahertz. So we'll say OK to that. Now, I entered all the motor specifications from the data sheet, and I calculated initial tuning values, and I used those initially for tuning. This should allow you to be able to tune the current loop and also phase the motor. So manual phasing was done so that we get, when we go forward, the counts go up, the red and black indicators line up. I had to invert the feedback device to get this alignment, but that's fine. Go forward and reverse. I used a minus 90 degree Hall offset or phase offset to get the proper commutation. So that's all done. The current loop, I did some current loop tuning and looked at the step response and the scope. But it's always a good idea to have a feel for your bandwidth. The current loop bandwidth should be about a kilohertz plus or minus a couple hundred. I've got a 900 hertz current loop bandwidth. Unless you're going to go crazy fast with lots of poles, that's sufficient for most of our control loops to be able to function properly. The peak and continuous current are calculated. This is the peak of the amps, not the RMS. So, RMS times the square root of 2 gives you the continuous peak. So that's where this number came from. And the 12 just happens to be the 12 amp peak drive limit that I have here. So that's fine. On the V loop, you can see the velocity limit. So this number should always be 10% greater than the maximum speed I want to command. There's some limiting going here. And the gain values are initially calculated, but I did some velocity loop tuning here. So we'll take a quick peek at the velocity loop tuning. So first, the current loop auto setup checkbox, hit start. You can see the current loop step response. Even if I'm hitting it with a large step, I get a well-behaved current loop here, so that's fine. I've got 900 hertz current loop bandwidth. So next I'm going to apply to the velocity loop, auto setup checkbox, so I can look at the current actual, but I'm going to chop the calculated acceleration down a little bit here. If I had an inertia or a load attached, I'd want to further reduce the acceleration because I don't want to hit a current loop while I'm tuning. My speed for 400 RPM is slow, but my back and forth rate might be a little high, especially if you have a load attached. So we're just banging it back and forth at a nice, comfortable commanded velocity. This goes through the limiter and becomes a limited velocity. And you can see the step response. There's a little ripple in there due to the motor's cog or detent, but that's okay. But basically what I do is I set the integral to 0 and look at the steady state error, shoot for the P term first. If the P term is too high, you'll break into oscillations, especially if your velocity loop pole is a 2-pole. So I move the pole out by making it a single pole, so the roll off is a little less. So you can see the oscillations. That was at about 180 hertz, somewhere near where the phase margin shifts as the pole is located there at 200 hertz. But with a higher gain, you get a stiffer velocity loop. I'm going to relax it a little bit so I can move my pole around in case I have a mechanical resonance in the system. It's always good to reduce it. And then we can start off with a high integral term. Again, we'll look at the integral windup at the end of acceleration to see if we get much overshoot. And it's not much. That might be a little bit high, but we'll turn it down during the position loop tuning. So I'm going to put in a value for acceleration here based on my counts per rev. So I have a rather high number, 33554432. 33554432 counts per rev. Auto setup checkbox again. 335543. 4423. There's 1 rev. I can set the trajectory limits. Let's hit 1,000 RPM. We'll go at 100 RPM here. So we can see that the tuning at the following error, the integral gives us a little amount to get to the steady state. I can increase the integral gain to get the steady state to settle in a little bit quicker. If I overdo the integral gain, then I could get integral windup. So taking a look at the P loop, I can see the gain multiplier was set by the calculations to 0.02. When multiplied by 1,000 pp, that gives us a nice stiff gain. I had to reduce the feed forward term. The calculated value is actually 0.015, which is not that much resolution here, so I have to decrease the feed forward from 16,384 down to 12,780 to get my following error to be 0 while I'm moving. One disadvantage of using so many counts per rev are limitations in the velocity calculations. So it's a 32-bit signed integer, so we have to be respectful of that. If we want to go at high speeds, then we'll knock the resolution down on the sine cosine, or just use the BiSS-B as it is installed on the encoder, and don't bother with the sine cosine. So at the end of the day, don't forget to save your settings to flash and save a CCX file with your tuning parameters. I've got this one saved as both BiSS-B and sine cosine, and my recommendation is just to use the BiSS-B without any sine cosine. Thanks for watching.